Hello, today I'm going to share our group's progress in physics-informed machine learning for flow and heat transport in 2025. All right, so our group's research goal is to study thermofluidic physics and discover effective designs of thermofluidic systems. So our group focuses on several physics phenomena, including flow heat structure interactions, multi-phase processes, and material morphology dependent heat transfer. And in order to understand these complex physics, we employ some visualization methods such as laser-induced fluorescence, particle image velocimetry. And in order to model such complex nonlinear multivariate physics, we also introduce AI ML methods such as physics-informed neural networks and generative adversarial networks. And finally, for the application side, when we apply our model and our understanding to optimize the system geometry, we employ a couple of design methodologies such as design for 3D printing, heuristic and adjoint optimization, and representative volume element. So first of all, why does the visualization of flow and temperature matter? Because many natural and engineering phenomena involve the flow and heat transport. So to understand such complex phenomena, it is essential to see beyond the visible. So here's an example of a tornado. So tornado is a really good visualization example of fluid dynamics, which visualizes the vortex in a certain local area. However, just by looking, this vortex is not everything. We cannot predict the trajectory of the tornado just by this visualization. So to better understand this phenomenon, we use satellite and wide area measurement to visualize the velocity distribution and also temperature distribution. So from this information, we can predict the trajectory and the precipitation of tornadoes, and we can save a lot of lives. And if you think about the engineering applications such as microelectronics, data center, EV battery, and turbine engines, we need fluidic cooling systems. And for effective designs of such systems, we need to understand the temperature and flow distribution in this system. So to understand the flow and temperature structures in those phenomena, our group try to understand where turbulence, vortices, viscous and thermoboundary layers are formed. And we use theoretical numerical models to predict the distribution of such fields. And we also, of course, employ experimental methods. And after that, we want to achieve design optimization to remove the inefficiencies or hotspots in cooling systems. And recently, we have been studying a couple of flow systems, such as transient natural convection flows, flow around pin fins, and convective boiling around electronics. And as we know, the visualization of temperature and flow has been done over decades and decades. But what are the still challenges in this field? So the most common way to visualize the flow and temperature fields is to numerically simulate such fields. However, if you're trying to simulate unsteady flow in complex and or large-scale geometries, you will realize that you need to generate millions or maybe like 100 millions of mesh. And to run the computation on such a large mesh system, even though if you employ high performance computing system, it's going to take weeks or months. And still, after just a couple of runs of numerical simulation, you're not still convinced by the simulation result. So due to these limitations, a lot of scientists still do physical experiments. So you can use particle image velocimetry system to visualize the velocity field around the structure of interest, where some people inject dye to understand the flow structure. However, many thermofluidic systems are not transparent because many of them are made of metal. So for this visualization, you need to make a separate systems that employ transparent wall. And also, this experimental setup is quite expensive. Um, so each system may cost as much as like 100,000 um, US dollars. So if you want to measure multiple field information, it means that you need multiple instruments. So it is going to be a very expensive setup that not many laboratories own at this time. So the visualization is normally limited one field information. So to tackle such challenges, my research group has been employing machine learning method. And I just want to briefly review the history of machine learning for thermofluidic research. So from my literature search, the machine learning has been applied to thermofluidic research in 1990s. And at this time, we simply did um, curve fitting between one input and one output variables. So if the relation between x and y variables are quite nonlinear, then it can be really difficult to find mathematical equation, mathematical form to express, to do the curve fitting. Then machine learning model can work perfectly for this type of application. In 2000s, now the machine learning has been applied for multivariate correlations. Just think about you have 50 input variables and multiple output variables. Then finding mathematical correlations is extremely difficult and maybe it's impossible. And for this type of application, machine learning has been working very well. And so even though machine learning is a black box model, you can still use it to predict the outcomes from multivariate inputs. And in 2020s, now the use of machine learning has been booming because of the advances in computing systems and also machine learning algorithms. So now we can express the relation between maybe millions of input and millions of output variables. For example, now we can approximate the concentration, pressure, and velocity fields in thousands by thousand pixel computation domain. And our research group has been focusing on physics-informed neural networks, or PINS framework. This is the machine learning framework that does not require extensive training data. So in this method, you put the XY t or spatial temporal coordinates as input, and you can make it to predict the flow fields such as temperature, XY velocity, and pressure fields. But instead of using abundant training data, now we use physics law or governing equations to train the model. And also you can employ the boundary conditions and you can still supply sparse observed data to constrain the prediction of your model. And this framework is really appropriate for most of the research laboratories because not many labs can access abundant experimental or data to train the deep neural network. So using the governing equation is a very efficient way to train the model. And PIN's framework has been applied to ill-posed fluid dynamics problem, inverse engineering, and multi-objective optimization problems recently. And my group has been applying the pins to infer unmeasured velocity fields from observed temperature data. So in many thermofluidic laboratories, measuring temperature it can be considered easy because the temperature is a scalar quantity, meaning that you only need to measure a certain value at a certain point. But if you think about the velocity measurement, you need to track the motion of particles, or you should do something similar. So compared to the velocity measurement, temperature measurement is much easier. And normally people employ single sensors such as thermocouple RTDs, and we can also employ optical approach such as laser-induced fluorescence, infrared thermography. And in this demonstration, we consider the following example: 2D transient natural convection in an enclosure. So in this demonstration, we use the following domain. So the temperature on the left wall is at high temperature, and the temperature on the right wall is low. And the top and bottom walls are insulated. And because of the temperature difference within the fluid domain, it will incur the density difference, and it will induce the buoyancy-driven flow motion. And this is really well observed also in your boiling pot or cooking pot. All right. So in this work, we train pin in this way. So the pin takes XY spatial and T temporal coordinates as input, and it outputs temperature, XY, velocity, and pressure fields. So at the beginning, of course, the model will predict very randomly, but you can train the model to produce reasonable outputs. So we used three different types of constraints. The first one was the non-dimensionalized governing equations, such as continuity, XY momentum, and energy equations. Also, we use the boundary condition to constrain the solution, such as no slip on walls and the wall temperatures already prescribed in the problem. And we provided the temperature data obtained from numerical simulation. So we collected the temperature data and select time moments in this 2D transient natural convection. So only with this information, now the neural network can predict the XY velocity and pressure fields. And let's take a look at a little bit more carefully about how we calculate the constraints. So to calculate the errors or residuals against the governing equation, we define the collocation points. So these are the points where we calculate the residuals against the governing equation. And instead of generating the mesh, we randomly sample the collocation points along XY coordinate space and also along temporal coordinate system. And we also calculated the loss against the temperature data given. Basically, you calculate the difference between the prediction of temperature by pin and the temperature data we provided using the CFD simulation. And this data loss is calculated on data points, which are shown as yellow symbols. And we also calculate the loss for the boundary conditions. And we calculate this along the boundary points shown as green symbols. So over the iterations, over the epochs now, we calculate these three losses, and if the loss is below a certain criteria, the pin is well trained. Okay, so now we use the trained pin to predict the temperature, XY velocity, and pressure fields. And now I'm showing the prediction at time equals to 1 second, 20 seconds, and 50 seconds. And we're comparing our pin prediction with the simulation result. So of course, at the beginning, the entire fluid domain is at initial temperature, very low temperature, which is around 0. And if after time evolves, now the hot fluid advex um, along the top surface of the wall, and then it convects over across the entire domain. And the density difference is generated, and accordingly, now you see the XY velocity and pressure fields are also evolving. And I'm also showing the animation on the right side, which shows the pin prediction at all the time steps. And we also compare this with the CFD simulation, and as you can see, the predicted fields are really close to the simulation, demonstrating that pin can be trained to predict an unmeasured field from measured scalar information. And we also try to understand the sources of errors in our pin. So although pin predicts pretty well, but it's not deterministic or exact model, so there are some errors still. So we first calculated the spatial gradients. So on the left column, you see the spatial gradients of x velocity at time equals to 1, 20, and 50 seconds. And you can see that there are regions with extremely low spatial gradients on the order of 10 to the negative 6 or 10 to the negative 5. And roughly these regions align with the high error regions. So this is actually well known in the machine learning community, and this is known as vanishing gradient issue. So if you have really tiny gradient values, so during the neural network optimization processes, this region causes a lot of errors. And now you see the errors are shown roughly along this region. And luckily, as time evolves in transient natural convection, the overall magnitude of gradient increase. Accordingly, the error magnitude decreases. And what you can see is, on the right side is the time derivative of velocity field. And in the transient natural convection, the time derivative decreases over time because at the beginning, the change of temperature field is rapid or velocity field is rapid, but at longer time now, the fields are really saturated, so there's not much change in the fields. So that's why you see a very stabilized gradient value. So, and our pin actually provided relatively large errors at the early period, and at the later period with the stabilized time moment, pin actually provided less errors. So from this result, now we can see that small spatial gradient and high temporal gradient are the causes of errors in pin prediction. And when you optimize the pin parameters, not only the original temperature magnitude, but also the gradient value of the temperature are used when optimizing our pin parameters. However, you realize that there are two different length scales involved in these two fields. So the regular temperature changes across the entire computation domain, meaning that the length scale of temperature is pretty large. However, the gradient value changes very rapidly across really short distance, meaning that there are some small scale features within gradient field. So basically, this 2D natural convection is a multi-scale problem. So in order to improve the accuracy, we expanded the input variables from just x, y, t to the variables, including the scaled input variables, and those are ABCs. So ABC are the scaled variables of x, y, t, which are divided by the scaling factors, deltas, and we obtain these scaling factors using multi-scale methods. So by handling two different length scale with these two different input variables, our multi-scale method integrated pin or MS pin reduced the mean errors by 6% and maximum errors by 72%. And in our recent work, we now use pins to infer velocity fields from concentration data. So in most of the laboratories, measuring measuring concentration is even easier than measuring temperature, because for measuring concentration, you only need high-speed camera. So my former student took this dye flow image using a GoPro camera. So he injected food dye in water flow and also injected dye as well. And these dye flow represent the underlying flow structure. And in many laboratories, people inject smoke to visualize the flow around wings or vehicles. And for more sophisticated and quantitative measurement of concentration, people use a laser-induced fluorescence technique. In this method, people inject fluorescence dye, which emits fluorescence when it is excited by laser or strong light source. So by measuring the fluorescence intensity locally, you can calibrate the concentration value in your flow system. And in this demonstration, we will focus on 3D intersecting channels looking like this. All right, so in this work, pin takes XYZ spatial variables as input, and then it predicts the XYZ velocity, concentration, and pressure fields as output. And this pin is constrained by the following non-dimensionalized governing equations, including continuity, XYZ momentum, and species transport equations. We also apply the following boundary conditions, such as no slip on walls, uniform inlet velocity. And we also provide concentration data obtained from simulation. So here, in this demonstration, we injected solute from the left and the bottom side of the inlet, and this solution mixes at the center, and they exit through the top and right side of the outlets. So they create a really unique characteristic pattern of concentration field. And with these constraints, now our pin predicts infer the unmeasured XYZ velocity fields. However, we encounter challenges in these 3D flows. So even though we employ very low Reynolds number 250, the flow pattern was not very simple or trivial for our pin, because the flow deflects, mixes, and rotates due to 3D effects and the mixing in the center region. So now we are seeing the simulation result here. So we are seeing the top view of pressure XYZ velocity fields. And the fields are changing because I'm changing the depth for the plane we are looking at. As you can see, the Z velocity field looks very unique, um, and it can be considered as complex. And we can also look at the cross-sectional velocity fields. And as you can see, the velocity fields are changing because I'm changing the location along this channel length. And yeah, predicting exact distribution of such velocity field is not really trivial. So our pin at the first time failed to produce the accurate flow fields due to the complexity of the flow fields. To tackle this problem, we introduce the domain decomposition strategy. This is a divide and conquer approach. So instead of solving the entire domain, we divided the entire domain into 9 subdomains. As you can see, the numbering here. So instead of having only one pin, now we have 9 different pins that solve each subsections. So each subsection is such very small, so it's not that difficult problem for pin. And to ensure the continuity across subdomains, now we apply 2 additional constraints such as interface matching condition and global continuity. Global continuity means that the sum of the inlet flow rates is equal to the sum of the outlet flow rates. And now I show the result from our pin with domain decomposition strategy. So on the top row, you see the prediction from CFD simulation showing the concentration, XYZ velocity fields. And in the middle, you see the prediction from pin. And in the bottom, you see the relative error. So now I'm going to play the video showing the field shown from the top view. And I'm going to change the plane from the type side of the channel to the bottom. All right. So now, as you can see, the flow pattern changes from top to bottom, right? And I just stop here and you can see that the flow patterns from pin is very close to the prediction from CFD, meaning that now, yeah, it is working. Okay, I will keep playing the video. And now, sorry. And now we are seeing the cross-sectional flow fields. And now we can see that the pin's prediction is now very close to the prediction from CFD. Yeah, showing this really, complex shape of the fields, right? So yeah, I will keep playing the video. So now we are changing the plane location from here to here. And the domain average relative error was the 3%. Okay. So yeah, pin is now also working. So we can infer velocity fields from concentration field. And we realized that how you obtain the concentration field is important. The easiest way to get the concentration field is that you inject your solute uniformly across the channel. So this is a cross-sectional view of the channel at the inlet. And then you can inject solute uniformly, something like this. However, the resulting concentration field will be really simple and monotonic, which does not represent the underlying flow pattern very well. However, you can inject the dye or solute locally, something like, just vertically on the right side or vertically in the center. So we name these two as vertical injection or center injection schemes. And resulting concentration field will be really characteristic, representing the underlying flow structure. And now we see the pin predictions on the right, and the uniform injection didn't really show the weak velocity field pattern near the outlet, and the Z velocity magnitude was very off compared to other injection schemes. So how you create the concentration field really matters for the performance of pin. And additionally, the size of data constraint matters. So we compared two different cases. First, the Corazon case, where you provide the concentration field data only within this cross region. And in the second case, which is called extended core case, now we provide data along the extended region outside the outlet. So we denote these two regions as padding. So because we provided more data, intuitively, PIN is supposed to perform better if the problem is very difficult. So on the right side, we compare the PIN predictions for the Corazon case and extended Corazon case. And we compare this with the CFT simulation on the left. And as you can see, the Corazon case had intensified flow rate, which is slightly off from the true field distribution. However, the extended core case provided a much better result. Okay, and next, now we're going to learn how PIN performs with the real experimental data. So in the previous two demonstrations, we employed numerically simulated temperature and concentration fields. So these scalar fields are errorless, so very clean, and so PIN can infer the unmeasured field much easier because the given observed fields are correct, exactly correct. However, in real experimental environment, measuring temperature and concentration field is likely to involve some errors. So let's take a look at our group's example. So again, we use laser-induced fluorescence to measure the temperature in fluid. However, you can create some wall defects. So by creating some scratches on the wall of your fluid system, right? Then the laser incident in your flow system can be deflected or distorted. And because of this, you'll see the vertical line artifacts. And also the laser may not be perfect. It can create some non-uniform intensity distribution in your area of measurement. Then it can create uneven background color, which is not the true temperature distribution. So I'm showing the example of very noisy temperature measurement. So my student made the flow channel using acrylic walls, acrylic plates, but unfortunately, when he cut the acrylic plates, he created a lot of scratches on the wall. So now we see so many vertical lines representing the errors. And sometimes we see non-uniform background color. Of course, this is not the true temperature distribution. Okay, so for this problem, we again train PIN like this. So PIN takes the x, y, t input variables, and it predicts the temperature and x, y, velocity and pressure fields. PIN is constrained by this continuity, x, y momentum, and energy equations, and additionally constrained by the boundary conditions such as no slip on walls and free slip on fluid's top surface. In our experiment, fluid didn't really touch the top surface of the channel, so that's why we apply free slip condition. And of course, we provide denoisy temperature data. And the expected output is the predicted temperature, pressure, XY velocity fields. All right, so now we see the example, okay? The result from our pin. So on the top left corner, you see the raw temperature measurement data, including the vertical line and non-uniform background color noises. But after pin take this input, now it predicts a really clean and correct temperature distribution. So the cold fluid passes the channel, especially in the center region. And we also predicted the corresponding XY velocity fields and pressure fields. And the domain average difference was less than 0.33 degrees C compared to the raw data. Okay. So Pin successfully inferred the unmeasured field, and also it corrected the noises in the raw data. So it's working, but there was a problem, which is extremely long processing or training time. So even though we use high performance computing system, it took 8.3 hours to process 30 seconds raw temperature data. So that is really far from our ideal situation. And ideally, we want to do this on real time. So, we are trying to address this problem employing transfer learning strategy. So, and this strategy is similar to how people learn. Okay. So when we learn really complex physics, we spend very long time. We can spend like a couple of hours to understand the underlying principle, and it will take again a lot of time to solve the problem. However, once we study such problem, and if we now try to solve the second problem that is similar to the first problem, it's not going to take such long time. And similarly, a neural network can learn very fast if it has been trained on the first problem, and if it is trying to solve the similar problem next. So in this case, the training time was reduced by 10 times. So think about it, if you do this work, do this process over and over, then the training time will reduce further. And for many people, um, naturally they can have questions about the validity of our inference. So is our pin really infer correctly? So to answer the questions, we compared our pin prediction against the CFD prediction. Unfortunately, our lab doesn't have experimental setup that can simultaneously measure temperature, velocity, and pressure fields. So for this heated flow phenomenon, we did numerical simulations that provide perfectly synced temperature, pressure, XY velocity fields. And we compared this with our pin prediction, pin's inference, and as you can see here, the predicted fields are really close to the CFD result, and the mean absolute error was below 16%. And we also compare our pin result with the particle image velocimetry experiment. Unfortunately, we were not able to measure these velocities simultaneously with the temperature data. So it was the separate, non-simultaneous measurement. But of course, the flow systems and all the flow conditions are the same, exactly the same. And unfortunately, we were able to see that the major flow patterns are really similar to our pin's inference based on the raw temperature data. So from this indirect validation approaches, we kind of validated our pin's predictions. So we hope that pin framework can be used to infer unmeasured flow fields and correct the noises in concentration and temperature measurement. So this is the end of this video, and hope that you understand our recent progress on pins. Thank you.